design, right? We had seen almost all of the chapter. So yeah, we had seen how, what data hazards are, and how to deal with data hazards. Easy ways but not so efficient ways, such as inserting NOPs or rearranging instructions at compile time, or more performance such as forwarding. So we had seen the various scenarios where we need to do forwarding. We also saw control hazards due to control dependencies such as branches or writes to R15, etc. And we had also seen techniques to mitigate it. In fact, a whole list of techniques here, such as stalling until the branch decision and BTA are available. Then we also saw branch delay slots, early BTA, etc. etc. So the stuff that we had discussed, where of course one possibility is to stall until the branch decision is available. The second one was branch delay slots, regarding which I got a couple of questions after the lecture or later on. In fact, in the lecture I had mentioned two. That is, you find two independent instructions to be inserted. Okay, that number 2 was just an example. So I had mentioned something along the lines of, the compiler needs to find two instructions which are okay to be executed no matter whether the branch is taken or not, right? That 2 was just an arbitrary example number given during the lecture, okay, which seemed to have caused some confusion. The number of branch delay slots is fixed in the ISA by the ISA designer. Okay, so for example, in the MIPS ISA, there is only one branch delay slot. So basically, the microarchitecture designer can assume that one instruction that comes into the pipeline after the branch need not be killed, even if the branch is taken. So it's a responsibility of the compiler to find one such independent instruction, which is okay to be executed no matter whether the branch is taken or not. Okay, hopefully useful, but at least the compiler has to guarantee that it is harmless. That is, executing that instruction does not cause any accuracy issue irrespective of whether the branch is taken or not. And hopefully that instruction is useful. If the compiler can't find any useful instruction, then of course the fallback option is to fill it up with NOPs. But basically, as a hardware designer, you don't have to worry about the immediately following instruction, right? You don't have to take the responsibility to kill it if the branch is taken. That's my point. Or that's the idea of branch delay slot. And there are other instructions and architectures like MIPS X, okay, which is a variant of MIPS, which actually has 2 branch delay slots. Okay, and then there are some other architectures where there are up to like 3. Okay, beyond 3 is very unpopular. And anyway, finding 3 such instructions which are okay to be executed no matter whether the branch is taken or not is already challenging. Okay, finding 3 completely independent instructions to fill up that slots. Yeah. And then we had seen early BTA where the branch was moved from the write back stage to the execute stage, right? Which reduced the number of troublesome instructions to 2. Only those 2 instructions which immediately follow it, that is, which would have entered the pipeline immediately following it, and right now in the decode stage and fetch stage are the ones which are supposed to be killed if the branch is taken. Now, if the ISA specifies that you have 2 branch delay slots, even this killing is unnecessary. Okay, because the ISA and the compiler will guarantee that the following 2 instructions are okay to be executed, whether the branch is taken or not. Okay, so you don't have to kill it. That's the idea. Okay, and that's the idea of branch delay slot. And here we are considering a case where there is no branch delay slot, and in fact, ARM instructions architecture does not provide for any branch delay slot. Yeah. So you have to kill the following 2 instructions, and you did that by flushing the pipeline or flushing those 2 stages, which is basically by asserting the clear of execute stage and decode stage, clear of decode and execute stage when the branch is taken, so that instead of the instruction from decode stage going into execute stage, it will be effectively an NOP that goes in. And instead of instruction from fetch going into decode, it will be replaced with an NOP. That's the idea. Okay, so that's the idea of flush. So there is no stalling here at all. We just replace the two instructions in decode stage and fetch stage with NOPs. Okay, provided the branch decision is taken in execute stage or the branch is committed in execute stage. Okay, now there are two terms that are used, stall versus flush. Again, these two terms are not entirely, I would say, standard. Different textbooks and different people use it, I would say, slightly differently, which could get a bit confusing, but once you understand, what's going on, it's not very difficult to figure out what they are talking about. Now, stall, here, the idea of stall, I mean, the terminology I use is to freeze a stage. Stalling a stage means you are freezing a certain stage. Yeah. So stall involves deasserting the write control of the pipeline register so that whatever you have in that stage will be preserved, will not be overwritten with something which is coming in from the previous stage. Flush involves asserting a clear of the pipeline register. So flushing is slightly different in the terminology that I use, where you are essentially asserting clear rather than deasserting the write enable. Now, if any stage is stalled, the previous stages also should be stalled. So we saw an example where a certain stage is supposed to be stalled, right? Where was it? In the load and use scenario, where the moment we realize that here we have an LDR R1 something something, and the following instruction, that is the one in decode stage, here is an execute. So decode stage has something like let's say R2, R1 something. So here you have a load and use hazard, right? And this cannot be solved by forwarding alone. We saw that even with forwarding, we are still having a misalignment by one cycle. So that one cycle gap has to be introduced between these two, correct? And that's why we deasserted the write control of the stage. And when you deassert the write control of this stage or this D register, naturally you have to deassert the write control of all the preceding stages. And here the only preceding stage is F, right? Because when one instruction is frozen, every instruction after that should also be frozen, after that in the code order. So that's when mentioned here. So if a stage is stalled, the previous stages also should be stalled, and the following stage should be flushed. So here, when we stalled the stage, D stage, we also stalled F stage, and we flushed E stage. So when load instruction goes from here to here, this hard instruction is not allowed to come in here. Instead, it will be replaced with an NOP. So you are allowing only an NOP to go into the E stage. Otherwise, what will happen? If you don't do this, if you don't flush the stage, you are essentially creating a copy of that instruction. So this hard instruction, in addition to getting stuck or being stalled in D stage, will also get copied over to E stage. So you have the instruction executing 2 times. Okay, which doesn't sound that bad, but we saw that there are problems with it. Like for example, the instruction, give me a moment. Yeah, so the instruction will get copied, and the copied version of the instruction, one copy, the first copy, the copy that goes into E stage will get executed using the incorrect data. So here you see, so you have a copy now, so you have an add instruction here as well as here, right? And the add instruction that is allowed to go into E stage, the copy that is allowed to go into E stage will execute with the incorrect value of R1 first. Okay, But then eventually it will be replaced by the correct version when this instruction, the instruction in decode stage is unfrozen. We freeze it only for one cycle, right? So the first copy executes incorrectly, the second copy executes correctly, which sounds okay because, well, eventually the wrong result will be overwritten by the correct result, right? So R2 will be incorrectly written first and then it will be correctly written. So eventually it will be corrected anyway. But there are problems. What are the problems? If the instruction writes to flags or causes exceptions, we have issues. What if that instruction is a division instruction? Then it might do division with an incorrect data. And what if that incorrect data happens to be 0? Then you have a division by 0, which in many instructions and architectures is an exception. And in Intel instructions and architecture, that, if I remember correctly, is the highest priority exception in the whole system. Divide error, which doesn't look very cool, right? So you are having an exception from an instruction which wasn't supposed to be executed at that point of time in the first place. There are also other issues. If you recall, I had mentioned another example, something like R, EQ, S. Let's say R2, R1. Now, that copy of that ADD instruction, which is executing based on incorrect data, will still end up setting the flags, which will be used by the following instruction, which is a correct version of the instruction, or the instruction that is getting executed at the right time rather than ahead of time. And that is not cool at all, right? So there are all these kind of issues if you create a copy of an instruction unnecessarily. Even though in first glance it might look okay because you may think, oh, the wrong result will be overwritten with the correct result anyway, so what's the big deal, right? But there are big deals in certain scenarios. Yeah? So effectively what you do is to insert an NOP between the instruction in the later stage being stored. So for example, in the load and use scenario, the instruction in the later stage that is being stored is the ADD instruction that is making use of the result from LDR, and the instruction in the following pipeline stage, which is your LDR instruction. So you are effectively inserting a bubble or a one cycle gap between the LDR instruction, which is the one in the stage following the stage that is stored, okay, and the instruction in the stage that is stored, which is ADD. So you are inserting a bubble or an NOP between them. So the instructions in the stages being stored are bounced in place. So the ADD instruction as well as any instruction that follows it are essentially bounced in place, not allowed to proceed. Okay, while the instructions in later stages of pipeline, for example, your LDR instruction and any instruction that is ahead of it in the program order, that is before it in the program order, are allowed to proceed. Okay, so here, any instruction that was in this stage, which is ahead of LDR in the code order, is allowed to proceed. And all these instructions, that is instruction in the later stage being stored, as well as all the following instructions in the code, that is in the previous stages of execution or earlier stages of execution, are all bounced in place. Good idea, right? So that's the idea of stalling, and the stalling is always done in conjunction with a flushing, so as to not duplicate instructions. Now, if any stage is flushed without stalling the previous stage, then the instruction which is supposed to go into the flush stage is replaced with an NOP, which is what happened with branch. We did not stall any stage at all. We did not deassert the write control of any stage. All we did was to assert clear here, assert clear here. So we are flushing those two stages. So flushing E stage and flushing D stage. So instead of the instruction from F going into D, you have an NOP going into D. And instead of instruction from D going into E, you have an NOP going into E. That's a net result. Yeah. So just expressing the ideas that we had already covered in English, that's all. So that completes our chapter on pipelining. Almost all modern processors, almost any processor which costs more than $5 to $10 will be pipelined. Pipelining doesn't help with the latency of a single instruction, but it helps increase the throughput of the entire workload. Okay, and in ideal scenarios, you can still have on an average one instruction or very close to one instruction completing every cycle. In practice, it will be at least slightly greater than one. The average number of cycles will be a bit more than one for sure, but ideally closer to one, while maintaining a fast clock cycle time. So your clock period is much smaller, or your clock frequency is much higher as compared to a non-pipeline design. Okay, and yet you are able to achieve a CPI close to 1. For a non-pipeline design, the CPI is always 1. Here you are able to achieve close to that, so not much of a hit in CPI, but a tremendous improvement in clock period or reduction in clock period. Pipeline rate is limited by the slowest pipeline stage, and we had seen again an example, our running example, where we had an imbalance in pipeline stage. So even though the total time period for an instruction originally in single cycle design, according to the numbers that we saw, was 680, we were able to bring it down only to 200. Okay, not 680 by 5, even though we had a 5-stage pipeline. That's because not all pipeline stages were requiring the same amount of time or the same critical path. So there was an imbalance in pipeline stage, and that's why our performance improvement factor or clock improvement factor is only 3.4 and not the ideal value, which is 5. And the time required to fill the pipeline and drain the pipeline can impact speed up for deep pipelines and short quadrants. Remember, if you have a 5-stage pipeline, you have no useful work that completes in the first 4 cycles. The first 4 cycles are the time required to fill the pipeline. And imagine if your branch was taken in the last stage. When the branch is taken, you have to flush all the previous instructions which are in the pipeline, right? I mean, all the instructions which are in the previous stages of pipeline, okay, which are actually in chord order the following instructions. So for a deeper pipeline, for a 30-stage pipeline, if your branch is committed in the last stage, you have to flush 29 instructions if the branch is taken. And that's again wasted time, right? So all these overheads reduce your performance improvement factor from what was ideal. And we also saw that pipelining can give us a lot of trouble, and we need to have appropriate hardware or software mechanisms, or a combination of the two, okay, which will reduce the effect or eliminate any incorrect execution due to hazards. So we had seen compiler inserting NOPs, which are a purely compiler approach. We saw forwarding, storing, etc., which are purely hardware approaches, or stuff like branch delay slots, which are in fact a combination of software filling up a certain number of slots, and anything above that being handled by hardware. So for example, if you have an ISA with 2 branch delay slots, up to 2 will be taken care of by software or compiler. Anything more has to be dealt with by the hardware. That's right. Yeah. So that is sort of a summary to pipeline processor. Now the story doesn't end here. The story continues into the next chapter. How do we extract even more performance? So first step, branch prediction. So we have added a few more stuff here and there onto the slides. There was nothing wrong with the previous slides. I just added some extra information, so you can perhaps annotate your slides with whatever I have highlighted in deep red color. Now, branch prediction. We saw control hazards are certainly harder to deal with. Data hazards except the load and use case, can be completely eliminated by forwarding or dealt with by forwarding. So that load and use required one extra, cycle to be wasted, right? But that was a worst case already. But control hazards are more problematic because at the point of compilation, there is no way for you to know whether the branch will be taken or not, right? And if the branch is taken, you probably wouldn't know where the branch is to be taken to. So you will end up most likely wasting some time in that process. So let's see whether we can save something. And the idea of branch prediction is to resolve branch hazards by assuming a given outcome. There is also a more standard term that is used, speculating. Okay. Speculation is basically guessing, right? So guessing a given outcome and proceeding without waiting to see the actual branch outcome. So you are making a guess on whether a particular branch is going to be taken or not. You are not waiting for the outcome to be clear. And you proceed with your guess. And later on, when you realize that your guess was wrong, do some cleanup. If your guess was correct, good for you. You didn't waste any time waiting for the unknown to be known, right? So there are various approaches. There are static and dynamic approaches. Whenever you hear about static and dynamic in computing, some of you might have taken courses where you talk about scheduling, right? Static scheduling techniques versus dynamic scheduling techniques. So what is the distinction between static and dynamic? Anything that is done without runtime information is static. So you do not make use of any information that is available at runtime, like for example the nature of data or whatever, and make a guess. This is typically done by the compiler, or it could be a policy that is fixed into the processor. But it's a policy that doesn't make use of any runtime information. That is called static. And let's look at static branch prediction. So the simplest two static branch prediction techniques are predict not taken and predict taken. Predict not taken basically predicts that branches will not be taken at all. A very unintelligent guess, okay? But still useful actually. And this is exactly what we already did. When we allowed the next sequential instruction to come in, you implicitly made a guess that the branch is not going to be taken, right? If your guess was that the branch is taken, if there is a branch instruction, you wouldn't allow the next sequential instruction to come in. Instead, you would allow some instruction from the predicted branch target address to come in immediately following the branch. So the next instruction that goes into the processor after branch will be from BTA, not from the sequential instruction screen. So we had taken the first approach, which is allow the next sequential instruction to come in, which was essentially guessing that the branch won't be taken. Correct? So continue to fetch instructions from the sequential instruction tree, and only when a branch is taken does the pipeline stall, or you essentially have to flush. Okay, here again, I should have used the term flush, but okay, like I said, the two terms are sort of interchangeably used depending on the context. So basically, you need to do damage control only when the branch is indeed taken. Otherwise, you will proceed as though the branch didn't even exist. So if the branch is taken, flush the instructions after the branch, which is what we just did, right? So when we realized that the branch was taken, the immediately following two instructions, which were in the two, earlier pipeline stages, were actually flushed. Now, our job was earlier fairly easy because we did the branch, or we committed the branch in execute stage. So only the two instructions in the previous two stages, which is fetch stage and decode stage, needed to be discarded or flushed. And instructions entering fetch stage and decode stage are completely harmless. Because in fetch and decode stage, you don't change the machine state anyway. But from the next stage onwards, or next stage onwards, the story is a bit different. Imagine a scenario where your branch was taken in the Imagine a scenario where your branch was actually taken in M stage. So your branch decision is committed only in M stage. So your code was like this, some branch here, and let's say the next instruction is RDES. So when the branch instruction is in M stage, your RDES instruction is in execute stage. Do we have a problem here? So right now, my branch is committed, let's say in M stage. I mean, in this hardware, in the original hardware that we saw, it was actually committed in execute stage. So the two instructions that entered the pipeline were in fetch and decode stage, which is quite benign. Okay, but things are not so benign when the branch decision is committed in M stage, when there are instructions in E stage. Because by the time the branch changes your program counter, and by the time you realize that instead of allowing this instruction to go in, you have to replace it with NOP. So basically, you have to flush M stage, E stage, and D stage. So by the time you realize that, the instruction in E stage would have already returned to the flags, because writing to flags happen at the end of E stage. So even when you kill it, it's already a bit too late. An instruction which was not supposed to be executed has already changed flags. And that's very bad news, right? We didn't have this problem earlier because we did that or we took the branch in E stage, but now the story is different. Now what if we go ahead with the original design, which is the branch being taken in W stage, which is how it was originally, right? Branch being taken in W stage means that your program counter is changed abruptly at the end of write back stage. And what if the instruction here is STR? And what if the instruction here is RDES? Before you could discard or kill STR, STR would have already returned to the data memory. And this instruction would have already returned to the flags. So two instructions which were at the wrong place at the wrong time ended up doing damage, which is not okay, right? So in such scenarios, what could you do? You have to recognize that problem early enough and stall if need be. Okay, stalling is one option. There is another option. Instead of committing the result, buffer the result somewhere. Put it in some temporary register rather than writing it to the destination, which is either your flags or your memory. Right? And only when the speculation is cleared, that is only when you realize that yes, those instructions were supposed to be there because the branch is not taken. Okay? So the assumption was actually correct. The assumption that the branch is not taken is correct. Then you can go ahead and write it. So either you have to buffer results or store the pipeline. So either of these two, or sometimes even a combination of the two, will have to be done. So basically, ensure that those flushed instructions haven't changed the machine state. Okay, if required, do some stalling or buffering or whatever. Yeah. Now, this wasn't a problem for us because, like I mentioned, the two instructions and the two stages that were eventually killed were benign. Nothing gets committed in decode stage or fetch stage. And then, since we made a mistake of bringing in the following instructions, we had to bring in the correct instruction, which is basically restart the pipeline at the branch destination, which will automatically be done. Nothing explicit needs to be done because once the branch instruction commits the result, committing the result is essentially changing the BC abruptly to your BTA, branch target address. So your pipeline essentially restarts at the BTA. And this is exactly what we had implicitly implemented. Okay, so we took care of all the problems here with our previous design already. Now the other possibility exists too. Okay, rather uncommon, which is have a fixed prediction that the branch is taken. So instead of predicting that it won't be taken, you predict that it will be taken. But then you have to have one additional prediction, which is you have to know where the branch will be taken to. It's not sufficient to make a guess that, okay, the branch will be taken. You also have to make a guess regarding where the branch will be taken to. So there should be some mechanism whereby you get a guess of BTA. Yeah? Otherwise, predict taken will not work because you don't know where to go to, even though you assume that the branch will be taken. Yeah? Now, why did I, did not make a big deal out of where and made a bigger deal of whether? Generally, answering the question of whether the branch will be taken is harder to answer or is harder to deal with as compared to figuring out where the branch will be taken, which is easier to guess. Yeah, because even for a specific branch instruction, so if you have something like say VEQ label, that label won't change at runtime, but whether EQ is true or not will change at runtime. Okay, so making any guess regarding where the branch will be taken to is a bit easier as compared to whether the branch will be taken or not. Now, in this case, neither of that actually changes at runtime because it's a static prediction technique. And so static prediction doesn't use any runtime information. It is used in simple processes because a non-static technique, as we will see later on, is a lot more hardware intensive. So if you don't want that much money to spend, predicting statically is a good option. And we saw that we already did it without incurring a lot of additional hardware, right? We require only minimal additional hardware to do predict not taken. And it is also many times used as a fallback when there isn't enough information for dynamic prediction. So we will see soon there is dynamic branch prediction, hardware intensive, but it typically requires runtime information. And when we talk about runtime information, we are typically talking about history. The last time that we looked at this branch, was it taken or not? That history won't be available the very first time you are looking at the branch, right? Typically, many instructions run in a loop, so your branch will be revisited over and over and over. The very first time you are looking at a branch, you probably wouldn't have any information or history at all to make a guess. And then you might fall back to static prediction. But subsequent times, since you have already built up a history, you can make use of that history, and that's your dynamic prediction. So it's typically a fallback option for dynamic prediction. Now, we saw predict not taken and predict taken, right? Predict not taken works well for top of the loop branching structures. That is where the branch decision, that conditional branch appears at the top. Example, if you are translating a for loop or a while loop more or less verbatim or in a direct manner to your assembly language code. For a for loop and while loop, the condition is checked at the beginning of the loop, not at the end. Right? So you can see here that there is a check and there is a branch, but that branch is to get out of the loop. For I is equal to 0, I less than n, I plus plus, right? So you are checking whether I less than n, you're checking whether I is less than n, and if that is not the case, you break out of the loop. So that condition is essentially to break out of the loop. So you have a BEQ out, which is the follow-out instruction. And this works well for, or predict not taken policy works well for this kind of loops. Why is it so? For a loop, the probability of continuing in the loop is much higher as compared to the probability of falling out of the loop. For I is equal to 0, I less than n, I plus plus. That's guaranteed to run n times, right? Right? So n minus 1 times you continue in the loop, only in the nth iteration you fall out of the loop. So the probability of continuing in the loop is higher, which means the probability of this branch being taken is very low. So predicting that you don't take the branch is advantageous. But this prediction, the prediction that we did, that is predicting that the branch won't be taken, doesn't work well for bottom of the loop branching structures. Like do while loop, where the condition is checked in the end rather than at the beginning. So here you see, you do a comparison, and then you take a branch to take the program counter back to the beginning of the loop. So the probability of this branch being taken is very high, because the probability of continuing in the loop is very high as opposed to falling out of the loop. So each time you keep predicting that the branch won't be taken, and much more often than not the branch will actually be taken. So you will be incorrect more often than not. Yeah. So it doesn't work for this kind of constructs. So if, let's say, the compiler has the knowledge that, okay, the microarchitecture designer will use a predict not taken philosophy, the compiler will likely generate a code which looks like this, which will improve the performance. Now there are other static prediction schemes. These two prediction schemes that we saw are very unintelligent prediction techniques, right? Following the same policy no matter what the situation is. You know, if somebody follows the exact same policy irrespective of situation, well, either he is enlightened or he is not very smart, right? Only two extreme set of people will follow the same policy irrespective of situation. So yeah, but yeah, practically that's not a very smart thing to do. So there are other techniques, like for example, there are situations where a compiler can insert a hint bit. So the instruction set architecture or your binary instruction format should allow for one bit to be used as a hint bit. So the compiler, based on its guess at compile time, inserts a 1 or a 0. So the moment the instruction is decoded, you already have the hint. You don't have to do any further execution before you know whether the branch is to be taken or not. Okay, but keep in mind, this is just a guess. So the guess is encoded by the compiler, and that information is passed to the hardware through the hint bit. The hardware will make its guess based on the hint bit. That's one approach. Okay, it actually was used, Pentium 4 processor had the ability to make use of hint bits. Okay, later versions of Intel processors do not, because it turned out that it wasn't as useful as they thought it was. Now, next one is again a not so intelligent guess, but more intelligent than this predict taken or predict not taken technique, where you make guesses, or you make a guess that backward branches are taken and forward branches are not taken. This actually works well in a lot of different scenarios. Like for example, it works well for both these. Because here, predicting that the branch is not taken is advantageous. And if you observe carefully, it is actually a forward branch. Right? So a forward branch in some sense is less likely to be taken. Whereas a backward branch is quite likely to be taken. And how do you know whether it's a forward branch or a backward branch? Just extract out one particular bit from your instruction, which is the sign of your offset. If it is 1, it means it's a backward branch. So you make a prediction that it will be taken. Yep. Very similar to hint bit, except that the sign bit of your offset is in some sense used as a hint bit. That's it. Okay. Again, used by some processors. Now, static branch prediction requires very minimal or in some cases no hardware at all. But as is with things which reduce or use less hardware, performance is likely to get a hit, right? So as branch penalty increases for deeper pipelines, so imagine you have a 30-stage pipeline where the branch is committed in stage 30. Every time you take a branch, or every time you mispredict the branch, you have to flush 29 instructions. Right? In addition to the trouble of making sure that these instructions haven't changed the machine state, etc., it can be quite troublesome. So there is certainly an incentive to improve prediction accuracy. And typically, if you have runtime information available, you can improve your prediction accuracy. So a simple static prediction scheme is likely to hurt performance, and with more hardware, it's possible to try to predict branch behavior dynamically, that is, using runtime information in the course of or through the course of your program execution. And there are a lot of different techniques out there. Dynamic branch prediction is one field where there has been quite a bit of research, quite a number of algorithms out there. But I will go through one simple technique, probably the simplest possible technique, which is just by maintaining a history table. All you do is to keep a log or keep a record of whether a particular branch was taken the last time it was executed or not. Yeah? But that table will typically have two elements. One element is, or one entry or one column in the table is a prediction regarding the branch itself. That is, whether the branch was taken the last time it was executed or not. Okay, I'll talk about this few lower order bits later. So that's one entry in the table, or one column in the table. The other column in the table is where the branch was taken to. So we maintain a history of whether the branch was taken the last time it was executed, and if yes, where was it taken to. So two separate columns in the table. But whenever you have a table, you need to have an index, right? What will be our index? Ideally, our index should be the program counter, because it's a program counter which tells us which instruction we are looking at. And only when we know which instruction we are looking at, we will know the corresponding history, right? But there is a problem with using program counter as an index. What is the problem? It's a very simple but a very serious problem. What would be the size of your table if your program counter is used as an index? For a 32-bit computer, your table will be 2 raised to 32 bits, right? And assuming that the last 2 bits are always 0, you are still looking at a table which has 2 raised to 30 entries, and that's a billion entries. Obviously, neither going to be very cost efficient nor going to be very fast, because anything which has a size of like 4 GB will be pretty slow. You will probably require a few clock cycles to read the table. And if you require a few clock cycles or a significant time to read the table, you are shooting in your own foot, because we were trying to make things faster. And that's why we need a table in the first place, right? So obviously the table can't be used. So what we realistically do is, instead of using the entire PC as an index, use the lower order bits of the PC as an index. Say the last 6 bits. instead of taking the whole PC, take the last 6 bits. Okay, the last 2 bits are useless. I'm talking about the 6 useful lower order bits. Then your table size will be 2 raised to 6, 64 entries, which sounds not too big. But you can obviously see a problem as well, right? What is the problem? There is only limited history you can store. There could be clashes. There could be 2 instructions with the same lower order bits. You might end up using the history from one instruction or another instruction. But that's a trade-off. You could get some wrong predictions because of that. But so be it. You can't help it. Yeah? So, yeah, some lower order bits are used. So the overall scheme kind of looks like this. Again, my own design, but well, the idea is fairly straightforward. So you have the PC. The moment you have PC, you will use the lower order bits of the PC. Let's say there are 6 bits or whatever, as an index to the table. The table has 2 columns or 2 entries per location, which is a prediction regarding whether the branch will be taken or not, and a prediction regarding where the branch will be taken to if the prediction is that the branch is taken. Yeah, so 2 entries. This is a 1-bit entry, and this of course is a 32-bit entry. Now these 2 entries control one of the entries act as a control signal to the multiplexer, where the other input to the multiplexer is PC plus 4. So if your prediction is that the branch is taken, instead of using PC plus 4, you will be using the predicted BTA. So your PC, instead of changing to PC plus 4, will change to the predicted BTA if the branch is predicted to be taken. That's about it for branch prediction. So the basic idea is quite simple. Okay, so the very next instruction that will come in will be from BTA. So if this is your branch, so let's say label. So here is your label. So you are making a prediction for label. So the next instruction after branch will be this instruction. The instruction from BTA instead of the sequential instruction. Whereas if the branch is predicted to be not taken, then this multiplexer will give or have a control signal of 0, in which case your PC plus 4 will go in. So it will be this instruction that goes into the fed stage immediately following branch. Yeah. Now, of course, this is not all. This is just the prediction part. But once you make a prediction, you have the responsibility to make sure that you check at some point later whether your prediction is correct or not. If it is correct, good for you, you wasted no time. Okay, the money invested was worth it. What if your guess was wrong? You have to undo the damage. So make sure that nothing gets returned, which is natural if your branch decision is available in each stage, right? Then the other 2 instructions wouldn't have returned anything anyway. You also have to restart the pipeline by changing your PC to the correct value. So let's say if you predicted that the branch was taken, you started this instruction and you would have also started this instruction. So this is now in decode stage, this is fed stage. And then it turns out the branch is not taken. So these 2 instructions have to be flushed, and your PC should be restored to the original PC plus 4. So that the instructions from here can continue because the branch was not supposed to be taken. And that's not it. You also have to change your table, because now your history has changed, right? So earlier your prediction was that, okay, the branch is supposed to be taken. But now you have to change the history or the prediction to not taken, because your prediction that it was taken turns out to be wrong, right? So you have to change your prediction to not taken. That's the idea. So that requires, of course, additional hardware, which again is not very hard to understand or implement. So let's say if you have this predicted ALU result. Why did I call it predicted ALU result? Because your BTA is supposed to be computed in your ALU. The result of your ALU for the branch instruction is essentially your BTA. But you are making a guess regarding BTA. And you are also predicting the PCSRC. So you are making a guess regarding what PCSRC will be. PCSRC is your branch decision. If PCSRC is 1, it means branch is taken. So you are making the two guesses, but you cannot just make the guess and not worry about it at all. You have to make sure that the guesses are propagated to the stage where you know whether your guess is correct or not. So this predicted ALU result, the prediction was made in 5th stage, has to be propagated or delayed by 2 cycles such that when the branch instruction reaches execute stage, your prediction is also available, or prediction is also made available to the branch instruction in execute stage. So here it was a prediction regarding BTA, here it was a prediction regarding the branch outcome, whether it's taken or not. Basically, just look at the association by name. I did not draw a line, not to pattern up the whole thing, but it's the same thing. Yeah. So you delay this as well as this by 2 cycles. And when your branch instruction reaches execute stage, the eventual outcome is computed, which is PCSRC. It is computed by your conditional unit, right? Your conditional unit gives you the outcome. And your ALU gives you the BTA. So both your actual branch outcome as well as your actual BTA are available. And this should be compared with your predictions. So you check whether your BTA is correct. You check whether your branch decision is correct. If there is a mismatch, well, we have a problem, right? If either of them mismatches, and that's what you do through here. Okay, so you essentially AND them up, and then you check, you realize that BTA is mispredicted. Why is there an AND gate there? You need to worry only about misprediction of BTA when the prediction is that the branch is taken. If your prediction is that the branch is not taken, don't worry about BTA, right? So if the branch is taken and if your BTA happens to be incorrect, then you have a BTA misprediction. Whereas if there is a mismatch between your branch outcome prediction, that is the question of whether it is incorrect, or the answer to the question of whether it is incorrect is predicted, then you have a branch misprediction. And if either of them happens, we have a problem and we need to flush C and D. Basically, the 2 following instructions should be replaced by NOPs. Okay, and you also need to correct the table or update the table entries. So you need to have the last few bits of PC. So here I have PCE, because the table entry that is to be updated corresponds to the PC for the branch instruction, which is now in E stage. So the PC itself has to be delayed, or at least the last few bits of the PC has to be delayed, so that you will have the correct index at the correct time. And you feed in ALU result, which is a correct BTA. You feed in PCSRC, which is a correct branch prediction or branch outcome. And you enable the right enables as well for the table. So if your branch target address is mispredicted, you need to have right enable asserted for the predicted branch target address, which is your predicted ALU result. And if it is your branch outcome that is incorrectly predicted, you need to change your branch prediction itself. That is, if earlier it was predicted to be taken, but it turns out it's not taken, you have to change that 1 to 0. Yep. Now your pipeline has to be started at the correct location. And for that, you need to have a multiplexer here, okay, which is controlled by PCSRC. So if PCSRC is true, it means the branch is indeed taken. But you have mispredicted things, right? So you have to restart the pipeline at ALU result, because ALU result is correct BTA, right? The correct place where the branch is supposed to be taken. So start from ALU result. What if it is the other way around? What if it turns out that the branch is not taken? Then you have to restart the pipeline at PC plus 4, right? So if the branch is not taken, you start it from PC plus 4. But it's PC plus 4E. Why? You save the PC plus 4 value so that it can be used to restore to original PC plus 4 later on. So you have to again, buffer or store all of this stuff. So at the stage when the branch instruction was in the stage, the corresponding PC plus 4 will be available as PC plus 4E 2 cycles later. And if the branch is supposed to be not taken, but you had predicted that it is taken, this is the value that PC should be restored to, because you should be fetching the next sequential instruction instead. Yeah. So that's it. Okay, so yeah, that completes the basic idea of branch prediction. Okay, and this is probably the most basic branch prediction circuit that you can do. Okay, which already sounds a bit complicated. Modern processors are far more complicated prediction circuitry. Now, your BTA or branch prediction could be wrong. What are the possible reasons why it could be wrong? Well, maybe this time it just happens to be wrong. Like for example, if the branch was supposed to be taken when or corresponding to something like this, in one time A happens to be 0. The next time when this instruction or statement is revisited, it might not be greater than 0. Just because the last time it was greater than 0 doesn't mean it has to be 0 or greater than 0 this time too, right? So it could just be data dependent. Okay, it could just be wrong this time. Or it could be because the last few bits could correspond to another instruction. So you looked up the table and looked up or got the entries corresponding to another instruction which happens to have the same lower order bits, which might not even be a branch instruction. Yeah. So that's possible. Of course, these can be fixed with appropriate additional bits, etc. To show whether it's a branch instruction or not, etc. Anyway, yeah. So with this design, it's very possible that you could end up getting the lower order bits from another instruction and making a misprediction. And in any case, we cannot compromise on correctness, though we can compromise on performance. We are not tossing coins here. We cannot just let things be if your guess is incorrect. You cannot just not check whether your guess is correct or not later on, right? So it's your responsibility as a hardware designer to make sure that you check whether your guess is correct. If it is incorrect, undo any damages post-production. And if the prediction is wrong, flush the incorrect instructions in the pipeline, restart the pipeline with the correct PC value. So you flush, assert flush, restart the pipeline at the correct value, and update the prediction bits and predicted branch target. Update the table entries. So all these three things have to be done whenever there is a misprediction. Yeah. Now, how many bits do you need? The more the number of bits, the higher the probability of getting your prediction correct, obviously, because you will be able to identify the specific instruction and the specific history more accurately. But a bigger table is lower, so there is a trade-off. And also, of course, a bigger table means more hardware. A 4096 entry table, which is actually quite big, you are using 12 bits from your PC, 4096 rows. That can give you 1% misprediction in some benchmarks, whereas in some other benchmarks it could be as high as 18%. So the exact percentage of accuracy that you get depends on both the prediction algorithm as well as your program behavior. Okay, a program which has a large number of for loops, etc., will tend to give you very good accuracy. Whereas if your program has a lot of if-else kind of situations which are data dependent, well, your prediction accuracy is likely to be not so great no matter which algorithm you use. Yeah? So a good algorithm can help improve, but it cannot guarantee that the accuracy will be very high. And 4096 entry table is very, very big. Okay, but and it gives you good accuracy at least in many cases, but requires a lot of hardware and it is also slower. Now let us examine things in a bit more detail. Now that we know how a simple branch prediction works, let us examine the performance in a somewhat real life scenario. Imagine you are looking at this particular loop. And let's assume that the original prediction is that the branch is not taken. And here we are talking about one specific branch, right? Let's assume that the original prediction is that it is not taken. You run through the loop the first time. Is your prediction going to be correct? Well, it depends on how many times the loop is supposed to be executed. And let's assume that the loop is supposed to be executed 10 times. For I is equal to 0, I less than 10, I plus plus. Yeah? So by the way, for loop is at top of the loop branching structure, whereas here is bottom of the loop. But yeah, you get the point, right? So the first time you will be wrong, because you predicted that the branch is not taken, but the branch will be taken. So first time you are incorrect. The next time you revisit this branch, your prediction will be that it will be taken, because last time it was taken, right? So the first time when it was wrong, you changed your prediction bit. So the next time, the second iteration, you will be predicting that the branch will be taken, and you get it right. And you will continue to be right 8 times. In the last iteration, that is the 10th iteration, your prediction will be that the branch will be taken. But it won't be taken, because that's the last iteration, we are going to go out of the loop. So you will be wrong. So what's your prediction accuracy? 80%. 80% prediction accuracy for a loop which is supposed to run 10 times. Yep. If the loop is supposed to run 100 times, your prediction accuracy will be 98%. So your prediction accuracy depends on the number n, the number of times it is supposed to be iterated. Yep. So yeah, that's one bit predictor. Now, do you see some problem with the one bit predictor? Was it the smartest way to do prediction? You changed your opinion just too fast. Okay, you got it wrong one time and you flipped. You suddenly changed your prediction, which probably isn't very good a behavior, right? You have to wait and watch. One failure shouldn't cause you to basically flip. And that's exactly what 2-bit predictors do. Okay, instead of changing opinion too fast, you change your opinion only if you get it wrong 2 consecutive times. Now this becomes a 4-stage or a 4-state state machine sort of scenario, right? Because, well, okay, it will be clearer once we look at it. So imagine a scenario where your prediction is that it's not taken. First time you get it wrong. Would you change your prediction immediately? No. You will still continue to predict that it is not taken. Next time you get it wrong again. And now you change because you got it wrong 2 times, right? So now you change your prediction to predict taken. So the third time you get it correct. Okay? All the way until 9th time you get it right. 10th time you still get it wrong because you will predict that it is taken, but it eventually won't be taken. So you get it wrong. So you have an accuracy of 70% for a loop that runs 10 times, which looks worse than before. Earlier you got 80% accuracy, right? Now it's down to 70%, which doesn't sound very great. But if you think about the fact that this loop is likely a part of a bigger loop, right? It's very unlikely that you will have one loop run exactly one time in the entire, or during the entire program execution. Okay. Useful data processing typically happens in nested loops, which are executed over and over and over, right? Most of the time your program spends, or most of the time spent by the program will be in some nested inner loop, and assume that this is somewhat an inner loop. You go out, come again, and this time what will be your prediction in the first iteration? Will it be that it will be taken or not taken? You will predict that it is taken, even though your last prediction was wrong. Your last prediction was wrong and you came out of the loop, right? You predicted that the branch will be taken, but it was not taken, and that's why you exited the loop. But one mistake will not cause you to change your prediction in a 2-bit predictor. So when the branch was not taken, your prediction will still be that it is taken. So the next time when you come in to this stage where the prediction is that it is taken, and you will be correct the first time itself, and you will continue to be correct 9 times. Only the last time you get it wrong. So in a steady state, you get 90% accuracy in this case, as opposed to 80% in the previous case. Only the first time you have a bit of a hit in performance, but if the same code is executed over and over, which is very likely, you will get a higher accuracy. Okay, and that is a manifestation or a direct manifestation of looking at more history in a way. So 2-bit predictor has more, or can store more history. Right? You have a history of whether it was mispredicted 2 times or not in a way. Only when it is mispredicted 2 times, you change your decision. Right? That's the idea. So BHD, instead of storing that single bit prediction, now stores the state of the state machine itself. Okay? And there are a number of different variants of this 2-bit counter or 2-bit predictor, but in general they belong to the category of predictors called saturating counter based predictors. Okay, think of it this way: you are in some sense counting the number of times the branch was taken. Yeah, and if it exceeds a certain threshold, you predict that it will be taken. If it is below a certain threshold, you predict that it is not taken. But the count doesn't increase beyond a point or come below a certain point. So it saturates. Yep. So it's called a saturating counter approach. Now that's about it for branch prediction. This is a basic, slightly more than basic introduction to branch prediction. But there are of course more advanced techniques available. Some of which are covered in this module CS52 something, I can't remember the exact module. Okay, advanced computer architecture. Now, just by looking at the local history alone, things might not be that accurate. Sometimes sometimes you have to look at the global history or the global trends as well. Okay, like in nested loops, etc., there is a high probability that there could be, I mean, if there is a misprediction in one inner loop, there could be a misprediction in the next outer loop, etc. So by looking at the global trend, you might be able to get more accurate prediction. Okay, so some of those modern predictors make use of both local history as well as global history. And when I talk about global history, it's not maintaining a history of every inner loop, but the trend of inner loops or inner branches. So the information from multiple branches will be combined as one single bit or set of bits. That is global history. Okay. And by making appropriate use of these two, you tend to get better accuracy. By looking at the bigger picture as well as the smaller picture for the specific branch that you have. Okay. A number of different predictors are available. Even some neural network based predictors are also used. Like some AMD processors use a perceptron based predictor. Even the article in Wikipedia about branch prediction already has some mention of some of these techniques. Yeah, if you are interested, please do it. But of course, these techniques cannot be that complicated either, because all this prediction has to be done typically within the same cycle itself, or within one or two cycles. If the prediction itself takes a long time, it's basically pointless. You are undoing whatever you are trying to do, right? So I guess it's a good time to take a break. Let's come back here by 7:30 and we'll continue. Predictor in most practical applications, but it's very hard to define one thing as a state of the system, because different processes might have different requirements for how much prediction can be, and generally you okay, so we had seen the topic of branch prediction. Now let us look at the next topic, okay, which is actually just one slide, deep pipelining. So branch prediction is one relatively advanced technique to improve performance. Next, deep pipelining. We already saw that in an ideal scenario, if you have n pipeline stages, your performance or throughput can be n times, right? Because your clock frequency in the ideal scenario will become n times, or your clock period will become 1 by n. But we saw that the reality is far from the ideal scenario. There are a lot of different issues which give us, or which causes the performance that we get from pipelining to be less than n, right? One is imbalance in pipeline stages. If you go by the numbers we had in the beginning of this chapter on pipelining, which is here.
instead of 680 coming down to 680 divided by 5, we saw that it came down only to 200 because for whatever reason, one stage hard to take 200 picoseconds, right? So now our improvement factor, instead of instead of your clock period coming down by 680, coming down to 680 by 5, only ended up being 200. So your improvement factor is 3.4, right? So you are getting only 3.4x performance, but in reality it's going to be even worse. You know why? Because of sequencing overheads. What exactly do you mean by sequencing overhead? When we talked about critical path was defined to be the longest combinational path, right? The path between two registers. So if I have two registers like this, the longest delay among all possible combinational paths is the one which limits how small our clock period can be. But that was after neglecting some so-called overheads. So if you look at that specific slide, which I won't go back to in the interest of time, I had mentioned that neglecting some of those overheads, this is the case. But in reality, you can't really neglect those, especially at higher speeds. Let's say if this is your clock. This is your clock. And at this clock edge, your flip-flop output changes. It propagates through a combinational path and then it is captured by this flip-flop at this clock edge. This flip-flop is what we call the launch flip-flop, and this is typically what we call capture flip-flop for this particular path. Yeah. Now, this much time was the time that we could take for combinational operation. But in reality, the change to the flip-flop output doesn't happen at the clock edge itself. It will take some time after the clock before the flip-flop output stabilizes. And it's not good enough for the data to stabilize at the clock edge. Your data has to stabilize a certain time before the clock so that it will be captured correctly by the capture flip-flop at the clock edge. So this time is what we call the clock to Q propagation delay. Sometimes simply called propagation delay, even though propagation delay standalone can be a bit confusing. So it's not a bad idea to call it clock to Q propagation delay. So the time taken for the Q, the output of the flip-flop, to change from the point you have the clock edge. And this time, or the time for which or from which the data has to stabilize before the clock edge, is what we call setup time. So your data has to stabilize a certain setup time before the clock edge for it to be captured correctly. And if your clock period is very, very long, then these times become negligible in comparison. But when you try to make your clock period smaller and smaller and smaller, which is exactly what you do with pipelining, then at some point it becomes very non-negligible. Okay, so imagine the overhead was 100 picoseconds. Okay, so it was 100 picoseconds here. Now what is your clock period? If the overhead was 100 picoseconds, what's your clock period? It's going to be 300. 200 for the combinational path and 100 for overheads. Right? So 300. So what is your improvement factor? Originally it was 680, or to be a bit more precise, 780, because there also this whole overheads are supposed to be added. So now from 780 you are bringing it down to 300. So your improvement factor is just 2 point something, even though you have 5 stages of pipeline. And this becomes more and more significant as you try and reduce your clock period by or further and further and further. And in order to have a certain clock period, you will end up having a lot more pipeline stages. So let's say if you want your pipeline or clock frequency to be 200, your clock period to be 200 picoseconds here. Okay, I want my clock period to be 200 picoseconds, of which 100 will be overhead, which means that the practical time you have available for your combinational circuit is only 100. Correct? Now, this will have to be split into two stages, right? Because one stage has practically only 100 picoseconds of combinational logic. So this will have to be split into two stages. And overall, you will have to have 10 stages to achieve a clock frequency of 200 picoseconds, assuming it can actually be equally split, which might not even be possible, right? So now to get a realistic clock period of 200 picoseconds, you need to have 10 stages. More number of stages means higher latency. And higher latency comes with a lot of issues. What are the issues? Whenever you have a branch misprediction, the number of instructions that you have to flush increases. Right? The time required to fill the pipeline is now quite substantial. Okay, it's like 9 cycles, each cycle being 200 picoseconds. So 1800 picoseconds just to fill the pipeline. Right? And a number of other issues. Okay? And some of which are related to the next point as well. Pipeline hazards. The more the number of stages, the more the number of instructions which are at various stages of execution at any given time. The more the number of potential hazards or interactions between these instructions. Right? Like earlier, you had to worry only about, for data hazards, worry only about the current instruction as well as the next 2 instructions. But what if there are 10 stages for pipeline? There are a lot more instructions that could have interactions or that could be affected by the result of one instruction. And whenever you have more of these interactions, you need to have more logic to deal with those. So more forwarding logic, consequently more muxes, and these muxes as well as the control logic, additional control logic themselves add to the delay. Right? So when they are added, your clock period wouldn't come down as much as you had hoped to. Because now you have more things in the critical path. The additional circuitry that are required to deal with multiplexers, etc. Or that are required to deal with hazards, which are multiplexers, etc. So your returns diminish further. So for every addition of a new stage, or for every attempt to bring your frequency down and down and down, the benefit that you get will keep going down and down and down. Like the improvement that you are getting when you go from 3 to 4, 3 stages to 4 stages, is reasonable. When you go from 4 to 5 stages, the improvement factor reduces. From 5 to 6, it's quite small. 6 to 7, even smaller. Okay, but the amount of hardware that you have to throw in, the amount of money you have to spend is quite high. Because with every additional stage, you have more interactions between instructions, more hazards, etc. More money needs to be thrown in. But the benefit you get goes down and down and down. So you have diminishing returns with increasing number of stages. So that's a problem with deep pipelining. So about 20 years ago, when I was in the computer architecture class, Intel used to come up with a higher and higher frequency processor every few months. The improvement factor was tremendous, and that was done by having deeper and deeper and deeper pipelines. So when I was in my final year of college, Intel had a 31-stage pipeline. the so-called net bus architecture. So whenever there was a misprediction, it was 20 cycles of penalty because the branch was taken at a stage where there were 20 instructions after the branch already in the pipeline. So 20 cycle misprediction penalty. And that was quite huge. So how did Intel compensate for it? By, of course, having more advanced branch prediction. Because with such a high penalty, it was imperative to have more complicated circuitry for branch prediction to improve accuracy. And that more complicated circuitry required even more hardware. And with hardware comes power, right? You have to throw in more power as well. So the TPU of Pentium 4 processor was 130 watts, if I recall correctly. Whereas for a modern desktop processor, it's about 30-40 watts. So it was almost like a heater in your room. Okay, and this was for the not so high-end version of Pentium 4. So yeah, that was a problem. Yeah. So at around mid 2000s, early mid 2000s, Intel realized that they can't really do this anymore. Okay. So at that time, Intel used to market their processors purely based on its clock frequency. After a while, people started seeing through that bluff. Okay. And of course, it wasn't good for Intel, so they went back to drawing board, abandoned Pentium 4 architecture completely, and started over. So that is deep pipelining. So most modern processors have a pipeline stage which is about 15. So something like 30 odd is not common anymore. A typical number is around 15, at most around 20, rarely about 20. And they resorted to other techniques for performance improvement rather than just trying to increase the clock frequency. And that's why even in 2005, we had already achieved a clock frequency of close to 4 gigahertz. And even now, most modern processors have a clock frequency around that. So it hasn't changed much in about 16, 17 years. Okay. The other technique is micro operations. The idea of micro operations is to decompose more complex instructions into a series of simple instructions called micro operations. So you could have a complicated instruction in the instruction set. Instead of executing that instruction directly, you take that instruction and split it into simpler instructions. Now, who does the splitting? In micro operations, the splitting is done by the hardware. The programmer doesn't see it at all. The instruction that goes into the processor is a complicated instruction. Okay, one example for a complicated instruction is this. This is a post-indexed instruction. Okay, somebody who is a hardcore risk fan, or somebody who is so much into or too much into risk philosophy, when they look at this instruction, they will say ARM is not a RISC processor. Because you are trying to do memory access as well as some computation. Basically incrementing the base register, which is an arithmetic operation, right? So you are trying to combine arithmetic and memory access into the same instruction, which is against RISC philosophy. And that's why ARM is not considered a canonical RISC processor by RISC purists. Now, an instruction can be complex, but your inner core of your processor can still be very RISC-like. So the front end of your processor will take this instruction in and will split it into two simpler instructions, which are executed by the inner core or the actual core of the processor. So the front end does some kind of a decoding or splitting of instructions. That's the idea of micro operations. So the micro operations are those operations or simpler instructions that are derived from complex instructions. And it is the micro operations that are eventually executed. It's very heavily used in RISC architectures. like Intel and AMD processors use it very heavily. Okay, their so-called front end is fairly complicated and dedicated to decoding or splitting complex instructions. Now, what is the advantage of splitting it into simpler instructions? The inner core of the processor, or the actual processing units within the processor, needs to deal with only simpler instructions, which will require typically only simpler hardware, are easier to pipeline, easier to deal with respect to hazards, etc. Yeah. So the front end as well as the core can be sort of designed independently. Now in this case, this is a post-index instruction which modifies both R1 and R2. Can this be implemented in your single cycle processor? Not without making substantial modifications like changes to the register file. Because right now our register file is designed such that it can write only one value. Whereas here you require two values to be written. So what you could do is split it up internally into two simpler instructions, which are possibly executed over two cycles. And then your processor internals need not be changed that substantially. That's it. The decoding is done by the hardware, so the programmer or the compiler doesn't need to know what is under the hood. Like I mentioned, Intel does it, but we wouldn't know what are the micro operations or simpler instructions your complex instruction is converted to. That's purely an internal detail. Intel probably wouldn't even want us to know. It's their design secret. The programmer doesn't need to know, doesn't need to care. Right? It doesn't affect the functionality. It only affects how things are executed internally. These micro operations need not even be valid instructions in the ISA. In this example, the complex instruction was split into two instructions which are still valid instructions within the ISA, which need not be the case. Because it's not something the programmer needs to see. It's not something the compiler needs to see. Got it? The advantage of micro operations is basically the advantage of sys processors, which is to do more things with less number of lines of code, which typically allows for denser code. The same program that is compiled for an Intel processor generally yields a smaller binary than it is for a RISC processor. You can express more things with less code, because each line of code or each instruction is in some sense more powerful. But you can also preserve the simplicity of RISC hardware for the inner core of the processor. Modern x86 processors, like those from Intel and AMD, actually decode instructions into micro operations and store it in a micro cache. So if the same instruction is executed again, and if the decoded version is already there in the cache, the time and the overhead required for decoding is avoided altogether. Yeah. Now, one common confusion people have is between pseudo instructions and micro operations. Pseudo instructions are also something like a complex instruction split into simpler parts. Right? Like for example, if you have a statement like LDR R1 is equal to X ABCD 1, 2, 3, 4 in ARM. This will actually be split into an assembler directive, which is something like, say, some label dot word ABCD 1, 2, 3, 4. And then there is an instruction LDR R1 label. So now this is a PC relative instruction, which will use PC as a base register with an appropriate offset. And the second part of it is an assembler directive. A directive to the assembler to place this in some memory location and call that location label. So something which looked complicated is split into two simpler parts. By the way, this is not an instruction, it's just an assembler directive. But in some cases, one instruction could be split into two instructions. Those who are doing RISC-V will find it even more familiar, because in RISC-V, pseudo instructions are used quite extensively. Okay, there are instructions like LA, load address, etc., which are implemented using two separate valid instructions. So LA is not a native valid instruction, which it's actually a pseudo instruction implemented using two instructions. Again, it's a case of something complicated split into something simpler. But the difference is, in pseudo instructions, the splitting is done by the assembler or compiler. It's done at compile time. So the programmer writes a complicated instruction which is split into valid instructions in the ISA at compile time or at assembly time. And in the eventual compile code, you will see it as separate instructions. So that's pseudo instructions. So it's very visible to the programmer or the compiler. If you inspect the eventual binary code, you can see it as separate instructions, which is not the case with micro operations. The splitting is done dynamically, not statically. It's done at runtime, and it's done by the hardware. And it is split into instructions which are not necessarily in the instruction set, and it's not visible to the programmer. You will not see any hint of micro operations in the compiling code. If you had some way to break into the processor and see what's going on inside, you could see it. That's all. So that's the idea of micro operations. Then the next major topic is multiple issue processors. The basic idea again is very, very simple, as is usually the case, but the exact details are extremely complicated. What is the idea of multiple issue processors? So far, whether it is a single cycle processor or pipeline processor, you fetch and decode at most one instruction in one cycle. You start only one instruction per cycle, at most. What if you could start more than one? That's exactly what multiple issue processors do. Fetch and execute more than one instruction at a time. That would mean you need to duplicate a lot of things to be able to deal with things in parallel. In pipelining, duplication was unnecessary because one instruction will be at one stage of execution at any given time, and no other instruction will be in that stage. So you don't have to duplicate a stage. You need to have only one copy of each stage of pipeline, which is now no longer the case. Every stage of pipeline needs to be expanded to deal with multiple instructions. So your register file will naturally require more read ports, more write ports. Your ALU will almost certainly need to be duplicated, because every instruction uses ALU. So if there are two instructions which are in execute stage at the same time, they require two ALUs, right? One each. And similarly, the data memory might also require more than one read ports or write ports. So yeah, pretty much every stage needs to be expanded. And your instruction memory should be able to again give you more than one instruction per cycle. So multiple copies of data path to execute multiple instructions at once. And now your CPI will be less than 1. Earlier, your best case CPI was already 1, because you could at most start one instruction per cycle. But now that you are starting more than one instruction per cycle, one instruction takes on an average less than one cycle to complete. Not from beginning to end, I am talking about the average for an instruction to complete. In steady state, you have one instruction completing every cycle in pipeline design, right? Whereas here you have more than one instruction completing every cycle. So your CPI will be less than 1. The average number of cycles per instruction will be less than 1. Okay, and since dealing with less than 1 is probably no fun, you use the term IPC. Instead of CPI, you use IPC, which is the reciprocal of CPI. The number of instructions which are completed per clock. And let's say in a multiple issue processor which can deal with 2 instructions per cycle, your ideal IPC will be 2. On an average, ideally 2 instructions will complete every cycle. But of course, like I said, real world is not ideal. Dependencies make it tricky to issue multiple instructions at once. So there is this term that is popularly used, ILP, instruction level parallelism, which is a measure of the average number of instructions in a program that the processor might be able to execute at the same time. So what is the number of independent instructions which the processor can execute at the same time? What is the limiting factor for this ILP? Dependencies. Some instruction might depend on the data that is created by a previous instruction. So the second instruction cannot be executed in the same cycle as first. Real dependency, data dependencies. Similarly, there could be control dependencies. Unless and until you know whether the branch is to be taken or not, you might not be able to fetch and execute the following instructions. Right? So data and control dependencies make it tricky to execute instructions in parallel. So in practice, for most programs, this number will be less than 3. You will typically not find more than 3 instructions which can be executed in parallel. And that's why most multiple issue processors are either 2 issue or 4 issue. And sometimes, in rare cases, 3 issue. So being able to issue more than 4 instructions is a lofty goal. Okay, so it's not that commonly attempted. Okay, for most state-of-the-art processors, the number is 4. Yeah. Okay. Then there is machine parallelism, which is the actual amount of parallelism that is available in hardware. ILP is mostly a property of the program. If a program is in such a way that there are a lot of independent instructions, your ILP will be naturally higher. Whereas, if the program is in such a way that all these instructions are sort of dependent on each other, very, very interlinked, then your ILP will be low. Machine parallelism, on the other hand, is purely about hardware abilities. It's a measure of the ability of the processor to take advantage of the ILP of the program. And that naturally is mostly determined by the amount of hardware you have, which allows instructions to execute in parallel. It's determined by the number of instructions that can be fetched and executed at the same time. Like I mentioned, issue width is typically a measure of machine parallelism. If it is a 2-issue processor, it has lower machine parallelism as compared to a 4-issue processor. That's right. But it's more than just the issue width. It also depends on the internal details. To achieve high performance, you need both. So trying to execute a program which has too many dependencies on a very highly parallel processor, that is a processor having a lot of machine parallelism, is still not going to yield you that good performance. Okay, the other way around too. An instruction or instruction stream or program that has a lot of ILP still will execute slow if your machine parallelism is not so high. Your hardware is not able to take advantage of the ILP offered by the program. And of course the performance won't be very good. there are two main categories of multiple issue processes: dynamic multiple issue and static multiple issue. Again, the term dynamic and static, which should already tell you that the first approach is the dynamic approach is mostly or is a runtime approach, which requires more hardware. Whereas static approach is a compile time approach, which will complicate your compiler or your programmer complexity, but on the hardware side, it will be simpler. Now, decisions on which instructions to execute simultaneously are made dynamically by the hardware. So, looking at instructions and deciding which can execute in parallel is something that the hardware decides at runtime. And like I mentioned, a very typical number is 4, but it can be between 2 to 8. Yeah. Most modern processors are superscalar. That should already tell you that eventually superscalar processors were more successful in the market. That doesn't mean VLAW processors don't exist, but they are mostly relegated to some niche applications like digital signal processing. Yeah, so most usual CPUs are superscalar, whereas VLAW processors do exist. For VLAW, all decisions are taken by the compiler at compile time. So the compiler will bundle the various instructions that are to be executed in parallel. So for example, if the compiler creates a bundle of 3 instructions, that 3 instruction bundle will look like one big instruction. And hence the term VLAW, very long instruction word. Because the 3 instructions are now not 3 separate standalone instructions, they are a part of one bundle, which looks like one big instruction. Now, whether it is VLAW or superscalar, using a combination of hardware and software, we need to be able to deal with the various issues, like for example, deciding on the number of instructions to execute in a particular cycle, which is the number of issue slots. Of course, we have to deal with data hazards, control hazards, as well as structural hazards. Data hazards are exactly the same as a single issue pipeline processor, just that it's more severe, because now we have more instructions at various stages of execution, which means there could be more dependencies between instructions which are currently being executed at various stages. Right? Like for example, in a 5-stage pipeline, you had a certain set of dependencies, but there were only 5 instructions at various stages. Now, if it is a 2-issue processor, you are looking at 10 instructions at various stages of execution. So more dependencies, more issues to deal with. So it's more severe, and the problem is exacerbated by the fact that typical programs don't have a lot of ILP. So the dependencies are typically a lot. And that has to be dealt with either by hardware or by software or a combination of the two. Then again, you again have control hazards. Same issue. Okay. Again, idea is the same. Severity is higher. And many a times you use dynamic branch prediction. So instead of waiting for the branch outcome, you make a guess and proceed. And that guess allows you a higher ability or an ability to deal with more instructions at the same time. In other words, dynamic branch prediction can in some sense expose more ILP or give you the ability to deal with more instructions, which otherwise wouldn't have been possible. Then we have resource conflicts or structural hazards. Again, much more, simply because you have more instructions. So functional units may have to arbitrate for result buses and register file reports. You know, duplicating everything blindly is probably not going to be cost effective. So in reality, a two-issue processor will not have a complete duplication of everything that was there in a one-issue processor. Okay, there will be some increases here and there, but not everything could be duplicated. Like for example, there might still only be one write port to the memory and one read port from the memory, from the data memory. So if there are two store instructions that are attempting to write at the same time, you have to somehow make one of the store instructions wait a bit. Okay, and that making one instruction waiting a bit is essentially called arbitration. Basically, two parties trying to do the same thing, but one party having to wait or back off is arbitration. Like for example, if you have a road, you have a door which is narrow enough that only one person can pass. If two people try to pass, well, it wouldn't work, so one person has to wait or back off. And that process is called arbitration. So same thing has to be done. So even register file, you know, having, for example, 4 write ports for a register file is probably a bit much. So you might only have a register file with, let's say, 3 write ports. So what if two instructions that are currently trying to read from register file are both instructions that read 2 inputs? For example, an str instruction and a dp register type instruction. And let's say you have only 3 read ports. One of them will have to wait. It would be okay if one of them is str, the other one is a dp immediate type. Then okay, you require only 3 registers to be read. But if it is dp register type plus str, well, one of them will have to be made to wait. So yeah, these kind of issues require additional hardware to check all these mechanisms and to, for example, make one instruction wait, etc., etc. So all this require a lot more additional hardware. The control logic as well as the data path are now a lot more complicated. Now, resource conflicts can be eliminated by duplicating the resource, but that comes at a cost. And in some cases, the resource itself can be pipelined. Like for example, multiplier unit or division units themselves can be pipelined. So it wouldn't wait for one division to complete before you start the next division. There could be multiple divisions at various stages of completion at the same time, which is probably more cost effective than having separate independent division units. Yeah. So the internal units themselves could be pipelined. Now let us look at an example. Yep. Here we have a 2-issue processor. So in an ideal scenario, that is on a good day, you will have 2 instructions completing every cycle in the steady state. Forget about the first 4 cycles, which is the overhead associated with filling the pipeline. But at the end of cycle 5, you have 2 instructions completing. At the end of cycle 6, you have 2 completing. Cycle 7, you have 2 completing. So in steady state, you have 6 instructions completing in 3 cycles. So your IPC is 2. And that's already the best case for a 2-issue processor. And as you can imagine, it's the ideal scenario. But let's look at something more realistic. Here you have a load and use case. So between the load instruction and the next instruction or next set of instructions, you need to insert a 1 cycle delay at runtime, which of course causes one particular clock cycle to have nothing completing. So here you have 1 completing, okay, 1 here 0, here 2, here 2, and here 1. So to complete these 6 instructions, you require 5 cycles. Because of dependency issues, you can't really push it ahead or any further earlier. So you will end up spending 5 cycles. So your IPC is now 1.2, far from the ideal value of 2. And that's because you have real dependencies. So here you can see there is a load and use hazard. Here there is a real dependency. So there is no way you could have bundled these two together. Right? Not in the same cycle for sure. This can only start 1 cycle after this. And similarly, this can start only 1 cycle after this. So real dependencies limit the IPC achievable. Is there any way you can make things better? Possibly you can push some of these instructions to this slot. And possibly the wasted cycle in between can also be utilized to execute some other instructions downstream. But that that requires your processor to be able to rearrange instructions. And in a superscalar processor, this rearrangement is done at runtime by the hardware. So the hardware has to check whether it is okay to rearrange and then rearrange. And even checking whether it's okay to rearrange is logically complicated. So that's the idea of out of order processing. So process instructions in an order that is different from the original program order. Rearrange instructions dynamically. And that will allow you to better utilize the parallelism that is available in the hardware, or IPC offered by, the ILP offered by your program. There could be independent instructions downstream, right? So make use of that, and that will allow you to increase your throughput. So that idea is called out of order processing. So for once, something being out of order is a good thing. It's a good thing for a processor. So it looks ahead across multiple instructions, and it issues as many instructions as possible, of course limited by the amount of machine parallelism. Yeah? So for a 4-issue processor, it can try and issue up to 4 instructions per cycle. And these instructions are executed out of order as long as there are no dependency issues. But now there are more dependencies or trouble than we had earlier. Earlier, with respect to data, there was only one type of dependency, which was what we call the data dependency, or to be specific, raw dependency. That is, one instruction having to read only after a previous instruction has returned. Right? That's your raw hazard. Example, let's say if I have L1 and L2. You are writing to R3 in the first instruction. The second instruction is reading from R3. It's a true data dependency. This was dealt with by forwarding. Right? And even in a superscalar processor, you can do forwarding, just that you cannot start the two of them in the same cycle. Okay, as long as this is issued after this instruction, it's okay. Yeah? But this is something that has to be checked by the hardware. The moment you see a true data dependency, you know for sure that there is absolutely no way L2 can be executed ahead of or even along with L1. L2 has to be after L1. So your possibility to rearrange L1 and L2 is gone. It doesn't exist. And there is no way you can fix this issue. It's not something that you try to even fix anyway. Because it's a true dependency. It represents a flow of information. Right? And this processing has to be done before you can do this. And there is no working around it. So a superscalar processor will not rearrange L2 ahead of L1 or even L2 along with L1. That's fine, reasonable, understandable. But now there are more issues. Look at this. Or this. What if L2 and L3 are rearranged? Is it okay? What if I schedule L3 ahead of L2? L2 is supposed to use the result from instruction L1. But now if L3 gets ahead of L2, L3 will write to R3. And L2 will end up using the value of R3 written by L3. So basically, this instruction using this value as the operand is a horrible thing to do. It's completely wrong. So this is called anti-dependency. And because of this presence of anti-dependency, a superscalar processor cannot and will not schedule L3 ahead of L2. So that rearrangement possibility is gone. Okay, so now this also acts along a diagonal, just like true data dependency, but in the other diagonal. This is a true data dependency. This one is a true data dependency. Whereas this one is on the other diagonal. So that's called anti-dependency. It's also called war hazard. Basically, L3 is supposed to write only after L2 has read the value. If L3 writes ahead of L2, it's not good. I mean, ahead of L2 reading it, it's not good. So that write by L3 should happen after read by L2. So it's called a war hazard or anti-dependency. Now the last one is wow hazard, right after write hazard. And that happens because L3 and L1 writes to the same location, R3. What if L1 and L3 were rearranged? Okay, forget about L2 at all. Assume that L2 was not in the picture, and assume that this dependency, or this is actually an anti-dependency, that was not in the picture either. So let's say this was something like R4. Okay, then the two dependencies that we saw earlier doesn't exist anymore. Now can I rearrange? So let's say if this is R4, this instruction doesn't exist. Now there is no true dependency, there is no anti-dependency between the two. Now can I rearrange? Answer is no, because there will be some instruction downstream which makes use of R3. That instruction should be making use of the R3 written by L3, not written by L1. If you rearrange the order, the value of R3 after these two lines are executed will be the value of R3 that is written by L1, which will be the value of R3 used by the instruction downstream. That's not okay. This instruction downstream should be making use of the value of R3 written by L3, not by L1. So you can't rearrange L1 and L3. That's because they have the same output. Yeah? This is called an output dependency. So now we have two new problems to deal with. anti-dependency and output dependency, which prevents us from rearranging instructions freely. Right? So these checks have to be done by the superscalar processor, and if any of these issues exist, you cannot rearrange anymore. Now let's look at an example. Okay, it's a different set of instructions. Oh, sorry, same set of instructions actually from here. Okay, different from here. Here it was a too good to be true scenario where there were no issues at all. This is a more real life scenario where there were issues, right? Now it's the same set of instructions, and you can see that in an out of order processor, this instruction can actually go ahead and fill up the second slot here for the two issue processor. And this instruction going ahead also allows this instruction to go a bit further ahead. And that's what happens here. So the OR instruction is now moved to the first clock cycle, second issue slot in the first clock cycle. And the following instruction STR can actually be used in the second cycle. The second cycle was a wasted cycle because of the load and use hazard earlier. So earlier you see, because of the load and use hazard between the LDR instruction and the ADD instruction, you ended up wasting one cycle. And now that wasted cycle is at least partially made use of by the STR instruction, which could get into that slot only because the instruction that it depends on, the OR instruction, could be pushed even one cycle ahead. Got it? So effectively, these two instructions are used to fill up those slots which would have been otherwise be wasted. But something still can't be rearranged. Like for example, there is absolutely no way this sub instruction can be pushed ahead because there is a wow hazard. Yeah? And this instruction cannot be executed ahead of this instruction because of this war hazard. So sub instruction cannot be pushed ahead of ART because of war, and cannot be pushed ahead of or even together with LDR because of the wow hazard. Yeah? There are no true data dependencies though. You know, if you look at what this instruction needs, R2 and R3 are not written anywhere here. So no true data dependencies, but because of output and or AND dependencies, you cannot push this ahead. Yeah? But still, the story is a lot better than it was here. Here your IPC was 2. And now you are at least making use of 2 unused slots. So the number of cycles that you need has now come down to 4. So you have 2 completing here, 1 completing here, 2 completing here, 1 completing here. So for those 6 instructions, you require 4 cycles. Now your IPC is 1.5. Better than 1.2 for sure, but perhaps not as good as we would have liked. So let's see how to make things even better. But before that, let's look at the anatomy of a modern processor. If you look at the diagrams available for modern processors, it will look more or less like this. If you go to wikichip.org, you can see the block level schematic of modern processors, and then compare it with this, and it looks quite similar. Because modern processors are out of order processors. I'm talking about high performance ones, not the ones you buy for $5 or $10. They are of course not even out of order processors, not even multiple issue processors in many cases. Okay. Yeah. So modern desktop processors and high performance mobile processors are out of order. So you have an instruction fetch and decode unit, which will look at, or which will take a bunch of instructions and look at dependencies and decide which ones can be issued in parallel. And depending on the nature of instruction, it will be issued to an appropriate functional unit. For example, if it is an integer operation, it will be given to an integer functional unit. Floating point to a floating point unit. Load store to a load store unit. Yeah. And branch, possibly for a branch handling unit. Now, it will not start executing in the unit immediately. It will go into a queue called reservation station. A reservation station is a place where an instruction waits for its turn or chance to be executed. The instruction will start executing when two conditions are satisfied. Number one, the unit should be free to start executing. The previous instruction which was getting executed in the unit is now done. So now the hardware is free. The second condition is all the operands should be available. What if it's an instruction R1, R2, R3, which requires R2 and R3? What if a previous instruction, such as a sub instruction, which writes to R2, is currently still executing or waiting for execution in another reservation station, or even in the same reservation station? Then the result is not ready. So this following instruction will wait in the reservation station until the preceding operation has completed and the result is available. And let's say if the preceding operation sub is executed in this reservation station, this ART is now waiting in this reservation station. So the moment sub instruction completes, the result is forwarded to the reservation station having an instruction waiting for it. So this process is essentially your forwarding, data forwarding. Right? The moment a result is available, take it from where it is available and give it to where it is required. So now you see this part basically operates in an order based on data availability rather than based on the original program order. Data and functional unit availability. Not necessarily in the same order as in the original program. Of course, true data dependencies sort of enforce an order and there is no working around it. Okay? But otherwise, you can execute things in any order. As long as the required data is available and as long as the functional unit is free. And eventually, the result, in addition to being forwarded, will also be passed to commit unit. And it's a commit unit which writes to the register files. So here the value of R2 is passed to the next instruction which is waiting in this reservation station. It's also passed to the commit unit so that it can eventually be returned to the register file. That's idea. Yeah. So issue unit tracks dependencies. Reservation stations hold instructions which are waiting for the data and the functional unit to be available. The functional unit performs the actual operation and the commit unit commits the result, which is basically doing the eventual writes to register file, etc. Okay, so this is how an out of order processor looks like. Now, instruction fetch and decode units are required to issue instructions in order so that dependencies can be tracked. So the instruction fetch and decode unit does not pick instructions randomly from the stream. If it does, it wouldn't be able to track dependencies anymore. To know what are the dependencies, you need to know the order. Okay? So this front end or the instruction fetch and decode unit operates in the same order as program execution order. So program order, yeah, not program execution order, program order. That is the order in which original instructions are. Then there is backend. Backend is required. Sorry, backend is required to commit results in order. Why so? Why should commit be done in the same order as program order? In other words, the value of R2 will be written and then the value of R1 will be written. Okay, here it is obvious because there were dependencies, but even if there were no dependencies, it will still follow the order. Like for example, here if it was, let's say, R4, then there is no longer any dependency. But still, R2 will be committed and then R1. Why should it be done so? In other words, the commit unit will commit results in the same order as the original program order. If exceptions occur, only those registers that are updated by the instructions before the one causing the exception should actually be updated. Right? So if you commit results in random order, you wouldn't know which were committed by the instructions before the exception, the one causing the exception, and which were the ones committed after the instruction causing the exception. Yeah? Second, if branches are mispredicted, those instructions executed after the mispredicted branch do not change the machine state. So it is a commit unit that will ensure that a misprediction will not cause a wrong functionality. So only when the commit unit realizes that yes, the branch is correctly predicted, will the results that are created by the instructions that follows it be committed. Which essentially means it will follow the program order. So an incorrect speculation is corrected by the commit unit. So although the front end, which is a fetch, decode and issue, and the back end, which is a commit, runs in order, in between it can follow any order. So the functional units are free to initiate execution whenever they have the required data available, and whenever, of course, the functional unit itself is free. Okay, so as long as the dependencies are respected, that is, the required data is available, you can execute it out of order, not necessarily in the same program order. And out of order execution increases the amount of ILP. If you follow the same program order, your ILP is limited. But having the flexibility to change the instruction execution order, you can possibly execute more things in parallel, which we just saw, right, in the example. So that is out of order processing. Now we saw that there were still some issues that were in some sense not properly dealt with, that had to be respected, but respecting those caused our performance to be pretty low. Those issues were var and wow. Like I said, row hazard is not a problem that you need to try to address. Forwarding already takes care of it. And it's not something you can even avoid. It's a true dependency. It's there, it can't be avoided. But the other two, they suddenly appear because we are trying to rearrange instructions. But if you have a closer look at those, you will see that those are in some sense fake dependencies, not real dependencies. Why are they fake? They manifested only because you are trying to reuse some storage locations. For example, the moment you changed this one to something like R7, now there is no longer an anti-dependency, there is no longer an output dependency. The problem is completely gone. but it was a programmer or the compiler which tried to reuse R3. And it is that attempt to reuse R3 that caused all the problems. You see the problem? Now with a different register being written, both output dependencies and anti-dependencies now vanish, no longer exist. So output and anti-dependencies are what we call storage conflicts. They manifest because of our attempt to reuse a storage location. In this case, R3. Now, why do we reuse it? We can simply avoid reusing it altogether, right? But the problem is, you have only finite number of registers. So, the moment a register is no longer required, it's natural to try and reuse it. Like for example here, what was the purpose of R3? The purpose of R3 was to pass a result from one instruction to the next instruction. So R3 exists to show that the result of this operation is essentially the input or the operand for the next operation. Once the next operation gets the required data, R3 is no longer required. And that's why we are storing a fresh value into R3. The new value stored into R3 has absolutely nothing to do with the value of R3 before. We no longer require this value of R3, and that's why we are reusing R3. That's the idea. So it's just a storage conflict. And why did that storage conflict come into play? Because we have finite number of registers. And in ARM, we say we have 16 registers, right? And many real world data require more than 16 values to be dealt with. So at some point you have to end up reusing. And even within 16, some of them are special purposes. So strictly speaking, not all 16 are usable anytime you want. That sounds quite limiting. And one register is like 32 flip-flops, which is not at all a big deal in basically that matter, right? Compared to the whole complexity of your processor, which has billions of transistors, 32 registers or 32 flip-flops seems no big deal. So why don't we just try and have more registers? Just duplicate the troublesome resource. Registers are cheap. Why are you limiting yourself to 16? Have 100 registers if you want. It's still not going to cost you that much. The relative cost of 100 registers to the total cost of the processor is not much at all. But what is the problem in having, let's say, 100 registers? You require 7 bits to address them. 7 bits can identify or address 128 different possibilities. So if you have 100 registers in your processor, you require 7 bits to identify one register. So identifying 3 registers will already consume 21 bits out of the 32 bits we have, leaving you very less number of bits for doing other things, like specifying other information, immediates, etc. So what superscalar processors do is to have a lot of physical registers, though logically there are only 16 registers, and keep some separate account of how the logical registers correspond to physical registers. So you provide additional registers that are used to track dependencies and establish the correspondence between registers and values. Here, this register is nothing but a value. The value that is the result of this instruction, which is passed to the next instruction. That was the purpose of R3, right? So, have additional registers which are dynamically allocated by the hardware in superscalar processors. So, modern processors have several tens or hundreds of registers. It's a big pool of registers. Not just 16, not just anything close, much more than that. when you need a register, take a register from the bank. Attach a label R3. There could be another register which is also R3. But the two R3s refer to two different values. In one case, let me just call it R3B. So this is also R3B because it's easy to see that they essentially refer to the same value, right? But this R3 is very different. It's essentially an attempt to store a totally different value. This R3 is actually different. This R3 was the result of some previous instruction. The purpose of this R3 is to pass the result of that previous instruction to this next instruction. So in some sense, this R3, and this R3 refer to three different values which have nothing much to do with each other. So they can be stored in three separate registers at the same time. Okay, so that is the idea of register renaming. The processor renames the original register identifier with a new register, which is not visible in the ISA. So the programmer does not write R3A, R3B, R3C. Because if the programmer writes it, you require more bits to identify the register, right? The programmer will simply write R1, R2, or the R0 all the way to R15, which allows for the programmer to use only 4 bits to identify the register. But internally, the hardware renames it to something like R3A, R3B, R3C, etc. So what the hardware does is, among the pool of registers, when you need a new copy of R3, take any free register and just name it as something like R3X, where X is something which is currently not in use. Okay, and release it back to the pool when the value is superseded and there is no outstanding reference to it. So at the point when the commit unit commits this instruction, R3B is no longer required. Once the commit unit is done committing this result and updates R4, R3B is no longer required. So now whatever was R3B is now marked as deleted or available. So now when the processor requires, let's say, an R5A or R6A, it can actually be named as R6A. So the same register which performed a function of R3B earlier is now named as R6A. So all you do is essentially attach a tag to a physical register, and that's now your R3 or R6 or whatever, okay, with some index A, B, C, D. So now you see all the registers that you are using in the lab. Well, it was fine for this lab, but that's not how modern processors deal with registers. The correspondence between the logical registers that are there in your assembly language and the physical registers which actually store data is not one-to-one anymore. It's not even fixed. Yeah, the same hardware which is R3B at some point could be R6D at some other point. Okay, so your entire understanding of registers so far is a lie. Right? So that's the idea. So that's called register renaming. And let's see how it can help. It's the same code which gave you 1.2 with an in-order processor, 1.5 with an out-of-order processor without register renaming. And now let's see how it is with register renaming. So if you look at this LDR instruction and this sub instruction, they both write to R8. Are they referring to the same value? No. So once you pass this value here, this R8 is done. So here you are essentially reusing R8 for something else. But in an In a processor where there is no register renaming, this can be executed only after this. Otherwise, you will have an output dependency or output hazard, wow hazard, right? But now, since they essentially refer to totally different things, you can rename. These values are held in totally separate physical registers. This is one register, this is a totally separate register. And by tracking dependencies, the front end knows this, that these two essentially refer to the same thing, but this one refers to something totally different. So it will do the renaming. So now this is R8A and this is R8B, and nothing stops you from executing this instruction and this instruction at the same time. Okay, so you are essentially eliminating that fake dependency or storage conflict and exposing the ability to execute more instructions in parallel. And now you see the only dependency that remains, only data dependency that remains after register renaming is true data dependency. Output and only dependencies are completely eliminated. And now, well, at least for this particular segment of code, you are able to achieve the ideal IPC, which is true. Yep. And this is how a modern processor really works. Okay, now there is a bit more to that story before we end. We will look at what is speculation. You already know one type of speculation, which is branch prediction. But I will show you another type of speculation called load speculation. And then we will look at VLAW processors and some comparisons. And then last part of this chapter is about hardware multithreading. We will see all of those in the next chapter, so next class. Oh, by the way, the next lecture where I will be lecturing will be in week 10. So the next lecture slot will be used for a guest lecture by someone from the industry. Okay, he is a senior who was in CG3207 a few years ago. So you can see or hear what happens in the industry from the horse's mouth. I will send you more details over the next 2-3 days. Okay, but I have a request to you. Okay, unless it is terribly inconvenient, please come physically to the class. Okay, in the past I have been in situations where I invited somebody from the industry, that person came, and there was hardly anyone that person had as audience. And it's quite embarrassing. Yeah, for me and for the university in general. Okay, so if possible, please do attend in person. The whole idea of having such guest lectures is so that you get to interact and hear from somebody who is working in the industry. So you can ask questions regarding the industry itself, regarding how things are in the industry, etc. etc. Yeah? It's a good opportunity, so please make use